Hello class and welcome to this video session. This time we will review the concept of mechanical energy. You will learn some types of this type of energy, and after that we will review the principle of conservation of mechanical energy. To understand all these ideas, it's important to recall some concepts that we have covered in previous sessions. So let's start by reviewing the forms of energy that we discussed before. We said energy comes in different flavors or different types, and in this list, you see some of the most common types of energy found in textbooks, physics textbooks. We will not discuss all these types of energy in this course. We will essentially cover the first four types of energy. We already have analyzed kinetic energy. We defined kinetic energy as the energy that is associated to the motion of objects, and we have a formula to calculate kinetic energy. So we see kinetic energy increases with the mass of the object and increases as well as the square of the speed of the object. We know as well theorem that we call the work energy theorem that tells us how kinetic energy is related to the work done on an object. And we know that when work is done on an object, the effect of that work on the object is to increase or decrease the kinetic energy of the object. So when positive work is done on an object, the object gains kinetic energy. If the work done on the object is negative, that means the object is losing kinetic energy as a consequence of the work done. So on the right side of this equation, you can see we have the final kinetic energy minus the initial kinetic energy. So the change in kinetic energy equals the work done on the object. In this session, we will review two types of potential energy: the gravitational and elastic potential energies. We will learn how these energies are defined, how we calculate them, and we will see as well how they relate to the kinetic energy of an object. We will learn as well how the potential energy of an object or system relates to the kinetic energy of that object or system. So let's start discussing the potential energy. Potential energy comes in different forms. We will review two of those forms, though other forms of potential energy exist. In these images, we see two situations where these types of potential energy are present. On the figure on the left, we see that the rock at the top, if it falls, it can produce a very strong damage on whatever is at the bottom of the cliff. So that rock has energy, and that type of energy is what we call the gravitational potential energy. The second diagram shows the coyote with a spring on his back, and he is ready to gain a very high speed from the energy stored in the spring. So springs have the capacity to store energy as well, and that's what we call the elastic potential energy. Elastic potential energy is the one that we find in rubber bands as well. When we stretch them, there is energy stored in it, and we can even launch objects with that tension created on the rubber band. So let's take a closer look first at the gravitational potential energy. The situation that you can see in this cartoon give us a good idea of the nature of potential energy. We have two rocks, one with a big mass at the top of a cliff, and one at the bottom with a smaller mass. Clearly, the big rock at the top of the cliff can produce more damage than the one that is at the bottom. And that is for two reasons. The first one is the height of the rock at the top, right? If it falls, it can produce a lot of damage, which, remember, is associated to the energy in an object. But it can produce more damage not only because it's higher, but because its mass. It's more massive, so a collision with that bigger rock will have more energy than the collision with a smaller rock. So gravitational potential energy then has two factors that can increase it, and those factors are the mass of the objects and the height of those objects. We can then write the gravitational potential energy as the weight of an object multiplied by its height. Note how the mass multiplied by g is clearly the weight, and then it's multiplied by the height of the object. Now, this type of energy is clearly related to the force the Earth exerts on object. So this ball shown in the picture has gravitational potential energy because the Earth is attracting that ball towards the center of the planet. If the Earth was not there, if the Earth could suddenly disappear, the ball would not have any potential energy. So we can then say that the gravitational potential energy is an energy linked to the system of the Earth and the ball. An important factor to keep in mind when we calculate the gravitational potential energy is that the height depends on what is the vertical reference level that we use to measure that height. So consider this ball now that moves from some initial height to a final height at the top of a table. We could measure the height from the ground. So we would have some initial height, some final height as well, different from zero, and we could then calculate the change in gravitational potential energy based on the change in the height. Another person, however, could have taken a different reference level to measure the height. Let's say the surface of the table, and that would be a valid choice as well. So for this person, the height would be measured from the surface of the table at the initial time, and the final height of the ball would be zero because it's already at the surface of the table. So when we analyze problems following energy arguments, what is really important is the change in the gravitational potential energy, not its value itself. So, as a consequence, we can choose the reference vertical level arbitrarily because changes in the gravitational potential energy depend only in the change in height, and the change in height delta H is independent on the reference zero level that we choose. It doesn't matter if we measure heights from the ground or from the surface of the table, the change in height will be the same, and thus the change in gravitational potential energies will be the same as well. So, which one should we choose? It depends on each problem. We would usually make a choice in a way that the initial or final heights are zero, because that way some terms will cancel in the equations and the math will be easier. Now, let's look at the other type of potential energy, the one that is stored in spring or elastic materials. Imagine you have this system of a spring and a mass located close to the spring. The spring is initially relaxed, and then we push the mass against the spring, and the spring is compressed. So the spring now has energy stored in it. And we know that if we let the spring go, it will push the mass and the mass will gain some velocity. So we clearly see how the spring releases energy. The energy in the spring is what we call the elastic potential energy, and it can be calculated easily. It's simply 1/2 multiplied by the spring constant times the distance the spring has been stretched or compressed. Since the change in length is square, it doesn't matter if we compress or stretch the spring, the potential energy in the spring will always be positive. So to summarize, we now know how to calculate 3 different types of energy: kinetic energy, gravitational potential energy, and elastic potential energy. Now, to understand the relation between kinetic energy and the potential energies, it's important to understand the concept of conservative forces. So, what is a conservative force? A conservative force is defined as a force for which work done by that force depends only on the starting and ending points of the motion of the object. So, if a force is pushing an object from position A to position B, the work done on that object by the force should be dependent only on the initial and final positions and independent on the path taken to go from the first to the last point. So let's see what this means in a more graphical way. Imagine we kick this ball from some initial height, so the ball naturally follows a parabolic trajectory and it hits the ground and reach the final position. We could as well do it a little bit differently and put a ramp so that the ball rolls down the ramp to reach the final position. The final position in this case is the same as the final position of the ball following the parabolic trajectory. We just changed the trajectory. Another possibility could be to use a ramp with a curved surface. So, if the ball follows the surface of the ramp, the path again is different. So, with these 3 possibilities, we could have that the ball follows 3 different paths to reach the same final position. In each of these 3 cases, the force of gravity does work on the ball as it goes from the initial to the final positions. And the interesting thing is that if we calculate the work done by gravity as the ball follows the parabolic path, the work would be the same than the work done by gravity when the ball follows the straight path or when it follows the surface of the curved ramp. So we can tell then that the work done by gravity depends only on the initial and final position and is independent of the path followed by the object. So we say that the force of gravity is a conservative force. Remember that according to the work energy theorem, when work is done on an object, kinetic energy will be taken or given to that object. Interestingly, when a conservative force does negative work on an object, it takes kinetic energy from it and transforms that energy in a type of energy that can be recovered later. So it So it keeps the energy in a form that can be used later. And that's why we call these types of energy potential energy. So that means that the conservative force can convert kinetic energy into potential energy, but later the process can be reversed and the potential energy can be converted back into kinetic energy by the conservative force. And you already know two types of conservative forces. The first one is the force of gravity. So the force of gravity can take kinetic energy from an object and convert it to gravitational potential energy, and vice versa. So look at the motion of the ball. When the ball is moving vertically, it has kinetic energy on the way up. The gravitational force does work and takes that kinetic energy and converts it into potential energy as the ball goes higher and higher. The process is then reversed, and when the ball is moving downwards, the potential energy is now converted into kinetic energy because the speed of the ball increases. And all this is due to the work done by the gravitational force on the ball. In a similar way, a spring can convert the kinetic energy of motion of an object into elastic potential energy, as we saw in the animation of the block pushing against the spring and losing kinetic energy, but converting it into elastic potential energy. The process, of course, can be reversed, and when the spring bounces back, the potential energy in the spring is released and converted into kinetic energy of the block. And now that we understand the relation between kinetic and potential energy, we can discuss the principle of conservation of mechanical energy. Imagine a system of objects. So we have springs, we have balls, we have moving cars maybe, and all these objects can interact among each other and exchange energy between them. If we keep this system of objects isolated somehow, let's say they are in an enclosure that won't let these objects interact with external objects, we know that the sum of the energy in each of these objects will be a constant quantity. So we say that energy is conserved as long as these objects are isolated from the external world. So these objects could have kinetic energy, gravitational potential energy, elastic potential energy, and they could interchange and transform these three types of energies among each other. But again, what the conservation of mechanical energy principle tells us is that the sum of these three types of energy will be constant in the system as long as it is isolated. Now, why do we specify that it's mechanical energy? Mechanical energy means the sum of the kinetic and potential energies. So we can write mathematically the principle of conservation of mechanical energy as the sum of the initial mechanical energy must be exactly the same as the sum of the final mechanical energy in the system. So there is no variation in the mechanical energy of the system as long as the system is isolated. In this formula, we have denoted the initial and final energies with an index I or F.